And let's share this. Okay, so we have these crucial equations for the neural network. And so that is how you compute the x's for layer L. This is 1, and then the activation function applied to the outputs from, are the inputs to the current layer. So these are the outputs of layer L, and they are basically just the activation function applied to the inputs. And then you have the equation for the inputs, which is just the transition matrix times the outputs of the previous layer. And so the other crucial things are the sensitivity vectors, and the sensitivity vector is, so this is where the gradient comes into play. So this is the derivative of the activation function with the inputs to layer L, and then this is entry-wise multiplied times WL plus 1, delta L plus 1, and then this will have sort of a bias entry at the top, so you need to trim it off. So we only go from 1 up to DL here. And then finally, there's the equation for the gradient itself with respect to the matrix WL, and this is just XL times DL, outer product. Okay, so we talked about the vanishing, or we've kind of alluded to the vanishing gradients problem. So what I want to do today is talk about sort of deep neural networks. There's a couple issues that we haven't talked about with just the material in the book. Like, for example, initializing the weight vectors in a neural network can affect performance a lot, and so that's an important topic. But that also kind of ties into deep neural networks. So a deep neural network is not anything mysterious. Some people argue that there's a lot of hype about it when it's really nothing new. And so it's just a neural network where there are 2 or more hidden layers. So you have the input layer, and then you have some number of hidden layers, and then you have the output layer. And it's deep if there are two hidden layers. So some problem, so for a long time people didn't know how to effectively make deep neural networks. So the problem is that you know, you're doing gradient descent, so you want to be updating, you know, for example, the update to the weights here will be like the existing weights, which is WL, and then when you do the gradient descent step, you're going to take away eta, which is the learning rate, times DE DWL. Okay. And the problem is that this quantity, the partial derivative of the error with respect to the weights in layer L, that might get extremely small. And that happened in the hand-worked example that we did. So when it also has a tendency to get smaller and smaller the further you go back. And so it just kind of peters out before it can get to the early layers. And so what happens is that as you do gradient descent, the weights here might learn very quickly. So the weights toward the front of the network will train quickly, but the weights toward the back of the neural network will be getting these very like weak attenuated signals, and it'll be very hard to train those. So there's some techniques that can help with that. But let's look at the math and see if we can kind of figure out why the gradients get small. So here's the equation for the gradient of the weights in layer L. So these outputs just are what they are. The reason that this quantity gets to be small is because delta L becomes small. And why does delta L become small? Well, partly because maybe, you know, it's the successor one was small, but one crucial reason is because of this term right here. So the sensitivity vector can get small because of this term, which is the derivative of the activation function. So why does the derivative of the activation function get small? So if you have a sigmoidal activation function, like the one that we've been working with, which is hyperbolic tangent, then so this is just a graph of the activation function itself. If SL tends to be out here, so this is, you know, here's SL, which is, you know, kind of big, then SL, the derivative of SL will be approximately 0 because the slope out here is approximately 0. Okay, and so now the training process has a hard time making any progress. So this will be like a slightly positive slope, you know, but the slope will approximately be 0. So we'll be trying to pull or adjust the weights so that this gets dragged back, maybe more towards where it should be. But because the slope is so slight, it will happen too slowly. And the same thing happens is if SL is kind of over here, then you get 0 gradients. So that's sort of the issue. And when this happens, this is called saturation, saturated activation function. Saturated activation, sorry. All right, okay. So one solution to this problem is to use non-sigmoidal activation functions that don't saturate, at least on one side. And so all of this stuff is like after there was a guy named Xavier Godot and a co-author who unfortunately whose name I don't know, who wrote a very influential paper about training deep neural networks in 2012. And they analyze a couple of things well, one of the things that they talk about is non-saturating activation functions. So let's give an example of that. So the example of an activation function like that is ReLU, which we have alluded to before. Let me turn off my ruler. So sometimes people write it like this. It stands for rectified linear unit, but I might just write this, you know. Okay, so I think, you know, the greatest compliment you can pay to an idea is to start writing it in lowercase, because then it's become, you know, so ingrained into culture and everything that it's just an ordinary word. So what ReLU is mathematically is just the, so for an input x, it is the maximum of 0 and x. So in NumPy or something, you can express this as, so you would do x greater than 0. So this would, now x is a vector here. So this will be a bunch of truth values. And then if you just multiply it times x itself, I think, yeah. Then where this is not true, you'll get false, and false is like 0, and so it'll zero out all the ones that are for which this condition is not true, and it will implement this. Anyway, the graph is what really helps you understand it. So it's just, if you put in something negative, 0 comes out. If you put in something positive, you just get a value on the diagonal. So ReLU looks like this. And so it has a few interesting properties. Obviously, it's not very sigmoidal. It is non-saturating on this side. So it's non-saturating for positive inputs. So the if this is your activation function, theta prime is always going to be, you know, bigger than 0 over here for the positive inputs. So it still is saturating over here on the left side, which can cause some issues. So this is actually always just equal to 0. So the tangents here are completely flat. So one thing to motivate like intuition about why this might work well in a deep neural network is, you know, we've seen like the ugly. Every neural network is just really some ugly mathematical expression that is a composition of the activation functions and, like, you know, linear algebra. So look at what happens if you compose ReLU with itself. So what is ReLU composed with ReLU? Try it two cases. So in the first case, suppose that x is less than 0. Then this output is going to be 0, right? And then you're going to get ReLU of 0, which is 0. Okay. All right. So we'll write it in conditional form. So this is 0 if x is less than 0. Now consider the case where x is greater than or equal to 0. Then the output here is going to be what for this first ReLU, the inner ReLU? So we're talking about an x over here. It's positive. So its output is just going to be itself. So the output here is going to be x. And it's going to be x if x is greater than or equal to 0. So this is ReLU itself. So the composition of ReLU with ReLU is itself. So if you have a deep neural network, then you're going to have deep compositions of the activation function with itself, you know, plus with some linear algebra stuff added in. So this is kind of a nice feature because it means no matter how many times you compose ReLU with itself, you'll still get the same activation function. If you do this same exercise with a sigmoidal activation function, what you'll find is when you compose it with itself, it tends to kind of squelch down like this. So the you know, the activation functions for the first few layers get deeply composed with activation functions from outer layers, and what it does is it kind of crushes the activation function down toward sort of just being 0. All right. Okay. So there are some upsides. You know, ReLU is fast. It there have been a lot of empirical studies just showing that it works well with deep neural networks. You can get better performance than with a sigmoidal activation function. But there are problems, and one of them is dying. It's called the dying ReLUs. So what happens is that some neurons effectively die, and it happens. So here you have the weighted. Let's look at just the weighted. So here's plus, and this becomes, let's say this is SLJ. So these are just the inputs to node J in layer L. And so here there's the ReLU activation function, and then here are the outputs. All right. So now suppose that these weights over here, kind of regret using that color. So these weights over here, these have, at some point in the training process, these weights have been adjusted so that this thing is a negative number. So suppose that this is like less than 0. And that's, of course, because of the outputs of the previous layer and the weights. So if that's less than 0, then what comes out in that case is 0. So this becomes 0. So now, once this output becomes 0, you know, if you look at how the update works for delta L, it's gonna the factors that are supposed to come through here and adjust these weights so as to kind of bring this neuron back to life are never able to come back through because of this 0. And what happens is you get a situation where this neuron just kind of starts to output 0 and then never stops. So they call that sort of ReLU death. And as many as half the neurons can die in the network, which is, I mean, it still works pretty well despite that in a lot of cases, but it's not something that you would want to happen. So one solution to that is to use something called leaky ReLU, and leaky ReLU is a lot like ReLU, except it gives these dead neurons a chance to come back to life. So instead of just having a completely flat activation function in the negative region, so this is what ReLU did. Instead, it gives a little bit of a slope here. And then for the positive part, it's just like ReLU. So this, you know, this branch of ReLU is just the identity. So this is X. And this branch is going to be alpha times X for some small alpha. And so what it's doing is so this is, you know, alpha is positive but very small. So this line, if you continued it, is just a line of some small positive slope. And so in practice in alpha that works well is like alpha equals 0.01, let's say. And the advantage to doing that is now if you have some point over here, the gradient is 0, so it's hard to for the training process to sort of adjust the weight so that you can climb out of this region. But now you can make a little bit of progress, even if it's slight. So now it's sort of non-saturating on both ends, and this tends to work better. So leaky ReLU is generally better than ReLU. Okay, and so you can take this even further. So in 2015, there was a study done on an activation function called ALU, which stands for exponential linear unit. And so this is sort of in the ReLU family. You still just have the identity function over here, but now you kind of bring it down sort of like this. So now there's a nice smooth curve, and so it slowly flattens out. And notice that it's differentiable everywhere. So that makes gradient descent work a little bit better. You know, with like this can be kind of herky-jerky because there's a non-differentiable point there. So if you do a little bit of gradient descent, it might jerk you over here, and then you do gradient descent over there, and it might jerk you back over there. And it might have a hard time sort of converging to 0 there. But this thing is smooth everywhere. So the gradient descent process tends to work better on a curve like this. And the definition of this function, ALU, is x for positive x. And it's alpha, which is an adjustable constant, times e to the x minus 1 if x is negative. So notice that this makes sense. So if you put in big negative values, then e to the x becomes like 0, and this just becomes alpha times -1. And so this is asymptotically minus alpha. So alpha is still some small positive constant. So alpha might be 0.1, for example. Okay. So this generally outperforms leaky ReLU. So often outperforms leaky ReLU, but it's slightly slower. So why does it work better? So it takes on some negative outputs. So if you look at ReLU and to a lesser extent leaky ReLU, most of the outputs are positive. You know, leaky ReLU does have some negative outputs there, but ALU will have more. And so that helps the average output be closer to 0. And so this helps the vanishing gradient problem. And it also has a non-zero gradient for negative inputs. And this helps with the dying nodes problem. So this helps to stop the neurons from dying. Okay, and finally, it's smooth everywhere, which speeds up gradient descent. Okay, the downside is that it is a little bit slower. So I implemented all 3 of these. Let me see if I can share this, I guess. And I was kind of comparing them. So I refactored the code that I gave you guys. And I changed it so that you can adjust. Sorry, let me just get to a good stopping place here. Yeah, so this is ALU. If you look at the equations, it should come back here, and let me just take you back to the previous page. So we wrote down these crucial equations. So there's only a few places where the activation function actually shows up in the code. This is the only place it shows up in forward propagation. And then in back propagation, it shows up here. And then I didn't write it, but there's also a base case for the sensitivity vector for the last layer. So the base case of the sensitivity vector is 2 theta s l minus y, which is the true label, and this is times theta prime SL. Okay, so there are only a few places in the code that theta actually shows up, and so you can just, and also theta prime, so you can just replace those with some other function. Unfortunately, the code that I gave you guys for project 6 has hyperbolic tangent kind of baked in, but for this code I took it out and then I just made it adjustable. So we're working here on the MNIST data set. So this is the I'm not sure you guys are looking at what I'm looking at. Let me just make sure. So this is for the MNIST data set, the handwritten digit classification data set that we've talked about several times. So we learn it. And to make it a binary classification problem, we're just going to try to tell the difference between 3 and other numbers. So, this will just be 1 if the digit is a 3 and -1 if the digit is a non-3. And then we scale it and add the bias column. And so here's neural network architecture. This means, here's the input layer, which has to be a size that is consistent with the data. And then we're going to do 3 hidden layers, each with 5 nodes. And then this is saying that there's just 1 output node. And then here we do stochastic gradient descent, and there are several options here, like the learning rate. This is Xavier initialization, which I'll talk about in a minute. So I also changed the stochastic gradient descent so that iterations now it's just the number of epochs. So we're going to do 5 epochs of training. We'll talk about dropout and beta in a second. This thing, regression equals false. So this is a classification problem, and you might think, yeah, regression obviously is going to be false. But it turns out, we've talked about this before, sometimes it's actually a good idea to turn regression on, even if you're doing a classification problem. And the reason is, if you're doing regression, then in the last layer, you make this last activation function just the identity function. And so that gives this a much simpler form. Then this just becomes SL minus Y, period. And there's no multiplication times theta prime. So one thing that might get you off to a bad start training is that this number might already be saturated at the end of the network. So the whole entire network might be producing an SL that's too big. Then you might be saturating at the very end. You might be getting a value here which is close to 0, and then that just that makes the training go very slowly, because it makes the deltas, the delta before this one will depend on that one, and it's like dominoes. They'll be small all the way down, and you'll get a bunch of small gradients. So even if you're doing classification, you might want to try changing the settings of your network so that the final activation function is just the identity, because then you won't saturate, and you'll definitely get a big number for the first sensitivity, and that will give you something to work with as the backpropagation pushes that value backwards through the network. And then what do you do with this? So this will just be a real number, something in the range minus infinity to positive infinity, and then you just threshold it with a sine function. And anyway, that's what you have to do even in this case. So either way, you have to threshold with the sine function to make the output of the network be something either +1 or -1. So instead of thresholding this, you'll just be thresholding that. So that's sort of a hyperparameter choice that you can always experiment with. Okay, so let's come back to the code here. So this is telling the difference between 3 and non-3 using the ALU function, and the test error here turns out to be almost 2%, so 0.017 here on the test set. Compare that to, so that here, this is just 1 minus that, because sklearn doesn't like to, instead of error, it tends to output accuracy. So accuracy is just 1 minus error. So this gives us an accuracy rate of 98.2 or 98.3%, which is not as good as random forest in this run. But that I ran it all again this morning to get you so that I would have all this loaded into memory. Before, it was beating random forest, so it's just because of the run this morning. But anyway, you can see that it's very competitive, and it does beat logistic regression. You can try the same thing, but now you just change theta to hyperbolic tangent, and you change theta prime. That's the derivative of this to be that, which is the derivative of the hyperbolic tangent function. And then the test error is 1.7, which is just so it's 1.77. So it's just a little bit worse than ALU. Then I did the same thing with, oh, wait. So now it's getting to train for a long time. And the test error goes down to 0.015. And then, but even with this longer training time on hyperbolic tangent, oh, sorry, I guess I just tried a bunch of things here. This is a little bit disorganized. So now it's getting beat again by ALU. So ALU is only training for 5 epochs now, and the test error has just gone way down. The reason that happened is because I changed the network architecture. So now each layer has, there are 3 hidden layers, but now instead of 5 nodes, there are 10 nodes. And so these are hyperparameter choices that you have to explore using a validation set. It turns out that this is a better choice. So then if you try hyperbolic tangent, hyperbolic tangent actually beats ALU here. And so that's been my experience playing around with this. You know, your professor sort of tooling around on the weekend with some toy data sets should not really be the deciding factor here. It should be these published works that have been very influential and validated by many others. But it's also true that people who publish things have an axe to grind. You know, they have like something to advocate. And I don't really feel like I understand these things until I implement them myself. So if you really want to get a feel, you know, I suggest you implement it yourself and try different data sets and see what happens. Here's leaky ReLU. Leaky ReLU does worse than either of those others at this task on the MNIST data set. And here's ReLU itself. And ReLU itself does not even converge here. So with leaky ReLU, I used an alpha of 0.1, but the documentation that I've read suggests that 0.01 is often a good choice, but I've found that it's not. So, you know, I guess you have to play around and try different different possibilities for the alpha parameter, which is used both in ALU and in leaky ReLU. All right, so now let's talk about initializing the network. So this is very important. It can make the difference between the algorithm converging, period, and not converging. So with a sigmoidal activation function, like let's just look at tan H applied to some dot product. So this is not our crazy neural network W. This is just the kind of, you know, linear coefficient vector that we've been playing with. So let's say that this is just something like this will happen at various points in the network. So if you initialize the weights to be too big, so if the weights are initially big, then this will start out being approximately plus or minus 1, and then its derivative will be approximately 0. And training will go very slowly, and the network just will never converge because the gradients, the progress with gradient descent goes too slowly. So it's clear that you want to initialize the weights to be small. One thing to consider here is the neural network error function is not convex. So with these error functions that we've been looking at so far in the class, they've all been convex, and so that means that there is just sort of one global minimum, and we approach it using a training process. But now with the neural network error function, there are going to be lots of local minima that are not absolute minima. So if you have an initial weight vector that starts the network off here, then your training process is going to roll you down into the bottom of this valley, but that's going to be a local minimum that might be far from the global minimum. And so if you randomly initialize the weight vector, which you should, running the network in different tries, you might end up with this W starting kind of all over the place here, and you might get very different results. So, you know, in practice, that's not a huge issue, but you should be aware that it's possible. All right, so we want the initial weights to be small. So the question is kind of how small. So the textbook suggests that you draw these weights. So this is our textbook, Learning from Data, because the advice in learning from data is a little bit at odds with the advice from hands-on machine learning with scikit-learn and TensorFlow. But this is what learning from data says. So it says that you should draw these from a normal distribution, and the normal distribution should have a mean of 0. So that's good. You know, that will make these things be approximately, these little weights will be approximately 0. And then there's this, the variance, sigma squared. So what should the variance be? The textbook gives the advice that the standard, or the variance, should be so small that sigma squared times the norm of x bar squared, sorry, so this is some training x here, and then this is the norm squared. This should be much smaller than 1 for all xn in the training set. So I've tried doing it this way, and I've never gotten good performance. So these are toy examples, but I don't know. I've you know, I've tried this strategy on like on MNIST. You know, MNIST is a fairly serious data set, and so this makes a lot of sense. Like the argumentation for this is very clear. I've just always found that, and you'll see in your code that I sort of make sigma 1. So obviously that depends on, I guess I'm just getting lucky here, and that the data that I've been using, it probably doesn't have any input vectors with high norm. So it might be that my strategy here of just using sigma equals 1, which has worked well in the data sets that I've tried, will be blown up if you try like an unscaled data set or something. But that's another thing. So with neural networks, you should always scale the data. And when you scale the data, these this will go down, you know, because all of the input values will be close to 0. Okay, so that is the advice of our textbook. So in the other book, Hands-on Machine Learning with scikit-learn and TensorFlow. So with the deep neural network stuff that has become popular over the last few years. So there's sort of 2 components to the fundamental difference between deep neural networks and neural networks before. One is the non-saturating activation function, which we have already talked about. The other is initialization. And so the initialization formula that was proposed by Xavier and his co-author, and then later by another researcher named He, is the following. So here, it depends on which activation function you choose. So let's suppose that you use the hyperbolic tangent activation function. And let's suppose that you're choosing your weights from a normal distribution. Then it should be a normal distribution with a mean of 0, and the standard deviation should be 4 times the square root of 2 over, so okay, so this depends on, this is going layer by layer. So this formula only applies to the transition vector, sorry, the transition matrix WL. So this is for the Lth layer. So these things will be chosen from a normal distribution with a mean of 0. And then the standard deviation is the number, I guess using our notation, this will be DL. So that's the, sorry, DL minus 1. That's the number of nodes in the input plus DL. That's the number of nodes on the other side of the transition. But if you use ReLU, then this should be sigma equals the square root of 2 times the square root of 2 over DL minus 1 plus DL. So when I made this change, I had a hard time getting it to outperform the standard initialization function, but now it's doing pretty well. I can show you a comparison here. So here's what this is a two-dimensional projection of the Wisconsin breast cancer data. So here this is using ALU, and you get a decision boundary that looks like that, and it has an accuracy of it has an error rate of 6%. So here's the same thing with the hyperbolic tangent activation function. You can see that for whatever reason, the decision boundary that gets found here is a lot more linear, and it just happens that the error is 8% here. And then with ReLU, you get, it's one thing with ReLU is that you get decision boundaries that are more obviously just compositions of linear functions. I mean, obviously, well, okay, so that's an interesting fact in itself. If you have ReLU as an activation function, then your neural network is just one big linear function, because everything about the neural network is linear except for the activation function. But in the case of ReLU, the activation function is also linear. And so when you look at the decision boundary that you get when you apply either ReLU or leaky ReLU, it will be like, conspicuously piecewise linear, which is kind of interesting. And the accuracy here turns out to be 0.7. So this fits the theory of the textbook perfectly. Like here you have ReLU outperforming hyperbolic tangent, and then ALU outperforming ReLU. Like I wish life were always that clean, But so that's what the theory says, and that's what actually happens here on this two-dimensional projection of the Wisconsin breast cancer data set. Okay. So now let's talk about regularization, something we haven't mentioned. So this is a very important topic. So we've seen that with just a 3-layer neural network, you can approximate any target function except for some crazy ones that would never occur to a normal person. So with all that power, there's going to be a real tendency to overfit. Even this model that we just looked at, that was like 3 hidden layers with 10 nodes each. Think about how big these matrices are, right? This is like, I don't know, I'm just being kind of crude here, but this is like 10 by 10. And then there's like 3 of those. So there's at least 300 parameters here. The MNIST data set is pretty big, so it can handle 300 parameters. But if you just have a data set with like 1,000 points or something, most of them are fairly small. That's going to be a huge number of parameters for a relatively small amount of data. Just as a rule of thumb, you want the number of parameters to be like, you want the amount of data to be 10 times the number of parameters. So that's easily not going to be the case if you have these big neural networks with these matrices with literally hundreds or thousands of parameters. So how do you do regularization? So it turns out that you can just do the weight decay technique that we talked about, just the generic augmented error. So let me just remind you how that worked. So we have the augmented error with the parameter set W is, so this is just sort of the end sample error. So this is how it does on the training set. But then you add a complexity penalty, and the complexity penalty that you add is the sum of the. So what we wrote before when we did this is like WI squared. That's when the weight vector was just simple. But now we have W arranged into these matrices, W1, W2, up to WL. And so we just adjust the notation to account for that. And so instead of writing it like that, now we write, so there's one index for every layer, and then for every ij entry in WL, you take into account Wij squared. And so there's also an L here. Okay. So when you do that, then when you're doing the gradient here, let's just look at instead of looking at the full gradient, let's look at just the part of the gradient that pertains to one of these matrices. So that's an easier way of thinking when it comes to neural networks. So if you look at the partial derivative of the augmented error with respect to just the transition matrix for layer L. So this is still a function of W. So obviously this will be ENW, and down here this is WL. So this 2 comes down, and when the 2 comes down, you're just left with the entries themselves. And when the parameters are arranged like this, something kind of beautiful happens. This just becomes 2 lambda over n times WL. So it's very simple and very easy to do in the code, because here's a scalar times this matrix, and these partial derivatives are both matrix derivatives, and so the dimensions of everything just works perfectly. So if you're doing batch gradient descent, what you've had is you've just been updating by subtracting eta times that, but now you just subtract eta times this entire quantity. This is for batch gradient descent. When you do it for stochastic gradient descent, you have to divide this by another n, because you're only doing 1/n of the work instead of looking at the entire data set, you're going point by point. So I don't mind. Should I show you? I think maybe I won't show you the implementation, because I might want to include that in a future project, so I don't want it out on the internet. But you might want to think about how you can implement it. It's not super hard. As you know from previous projects, adding regularization is surprisingly easy, because you just take your gradient function and then you just add in this term. So it's pretty simple. But just heed my words, because we're using stochastic gradient descent instead of batch gradient descent. You'd have to divide by another n there. Either that, or you can make an adjustment once every epoch, is I guess another thing you could do. If our stochastic gradient descent goes by epochs, so you could actually use a stochastic gradient descent epoch to just actually create or to implement one step of batch gradient descent, and then you could make this modification at the end. Okay, so there's another kind of regularization called well, there's early stopping. So that's just a generic technique that we've talked about before. You can stop the gradient descent process early, and that will improve stop overfitting from happening. There's also this idea called dropout. So I tried to implement dropout. I'm pretty sure I made a mistake, so I don't want to show it to you. But the idea with dropout is to turn off half the nodes chosen at random. So you randomly select half the nodes and then turn them off during each training iteration. So I'm going to put sort of double exclamation mark here because it sounds like it would be a terrible idea. It's like you're trying to learn something, but you're having a stroke like every second. But it turns out it makes the network simpler and more robust. The book compares it to a workplace where at random half the employees don't show up every day. So you can imagine that an organization like that would be a lot more resilient and not crucially dependent on any particular person, because any given day there might be a different sort of subset of people doing that job. Google tried to patent this idea, actually did patent this idea, but some people have pointed out, if you look at the Wikipedia page, there was a similar idea, of course with a different name, because it's just a made-up name. But the same idea was proposed in the 90s under a different name. So this is kind of fun. Unfortunately, our book, Hands-on Machine Learning with Scikit Learn and TensorFlow, it doesn't say exactly what this means. So what I did, I think, is not right. But what you could do is, before you do the forward-backward propagation step, you could just go through all of these matrices and then so zero out, choose for each matrix here, let's just look at WL, choose 50% of the rows in here at random and then just zero them out. So that will make those nodes completely irrelevant to the learning process for this iteration. So then you do one forward step and one backward step, and then you choose different nodes to kill the next time. So I'm pretty sure that will work. But the book doesn't say precisely what it means, and I didn't have time to read the research article. Why didn't I know it anyway? Well, it's a new idea, and when I was in your position in like 1997, this was far in the future. So, okay. So one more thing that I wanted to talk about that's exciting is multi-class classification. So neural networks can naturally do this. So we've been sort of drawing them so that there's a single output node. You know, you have an input layer, and then several hidden layers, and then all of these funnel down to just one output node in the last layer, L, and then that's the output. But it turns out that the entire process that we've described here will work just fine if there are multiple nodes in the output layer. So then maybe there's, you know, a whole bunch of these things, and you get 3 outputs. So here's layer L. Okay. So I did this with the MNIST data set. So you have to encode the Y's, though, is the problem. So with these 3 output nodes, the way I've done it here, let's suppose that the values that the Y's take on are just like 0, 1, and 2. So to make this idea work, you don't use these naked numbers. You have to do a binary encoding of them. So 0 will become 0, 0, 0. 1 will become 0, 1, 0. Sorry. Oh yeah, sorry, I'm encoding it wrong. So this should be 0, 0, 1. This should be 0, 1, 0. And this should be 1, 0, 0. Or you could use -1s too. This could be -1, -1, -1, -1, 1, -1, 1, -1, -1. So now when you're training, if you look at what's happening with the only thing that the only part of the code that has to do with the last layer is the initialization of delta L. which is theta, sorry, it's 2 times theta of SL minus y times theta prime SL. So the way, it's just been our convention so far that SL is like a scalar. Because the way we've been working, there's only one output layer, and so there's just one SL here, and so it's essentially just a number. But now you can think of SL as being like a vector quantity. So it's these, it's these 3 inputs instead of just one input. So and now if y is a vector quantity too, so now y is like this, for example. So now this entire thing becomes a vector quantity, and you get different values corresponding to the different entries here. So let's say that this is such that it should be 0 on coordinate 1, but it's actually not. Then you'll get a high penalty on this wire that will percolate backwards. But if the middle wire is outputting a 1, which is pretty close to the value that it's supposed to be, then there will be no penalty transmitted back on this one if it's outputting what it's supposed to. And then so it's like each one of these outputs will be independently punished. So changing the code to make this work is pretty trivial. And here I did it with multiclass here. sklearn has something called label binarizer, which does exactly this process that we were just talking about. So so here's what I've done. Maybe first let me just show you the first few y's. So y is this. Okay, so it's 5, 0, 4, 1. And now look what happens to when we look at the encoded versions. So 5 becomes, it's all negative 1s except that there's a 1 in the index corresponding to 5. And here there's a 1 in the position corresponding to 0, but all the other ones are -1. And here there's a 1 in the position corresponding to 4, etc. So that's just an encoding of the ordinary labels. If you want to go back to the original, then you can do an inverse transformation, and then this takes you back to the original labels that came with the data set. So I did all this. Now, when you declare the architecture, you have to be careful about the number of nodes in the last layer. So until now, every time we've said that the architecture had just 1 node in the last layer, but now we have 10. So you can do training. So if you just look at so here's the result. It was like on the test set, it's 92% accuracy. But let me show you kind of what comes out. This might be a disaster, but I hope not. Let me comment some things out here. So I've got this G train, and let me just show you a couple of these G trains. Let's just look at the first 4 then. And I guess it's doing the prediction here, but hopefully it will actually output something. But anyway, the thing that you have to consider is now when the network makes a prediction. Whoa, look at that. You know why that's happening? I think that's because just the last thing I tried didn't converge. Let me turn all this stuff back on, and then I'll just keep jabbering while it runs. So now the predictions, there's going to be 1 prediction for each output wire. I don't want to wait for this thing to go for 10 iterations. I'm going to change it to 3 iterations. Oh no! Do you hate it when this happens?
Yeah,
when
you're inserting.
keyboard
Yeah,
starts
I
like
hate when that happens.
overwriting instead of
Because you have insert turned on. I think that's why.
Only when you're lecturing, probably. Stupid thing.
Just click insert on the keyboard and that
key.
should fix it. Yeah, there you go. Did that work?
There it goes. Dropout. Okay. So now hopefully it will go. So in the picture that we were looking at on the other page, when this network now makes a prediction, the prediction is going to be a vector of values. There's going to be a prediction for this output, for this output, for this output. And so you have to find some way of combining them to reduce it to, you know, either some natural class like 0, 1, or 2. So the output here might look kind of weird. It might be like -2, 1, -3, or something like that. And the way to make sense of that is that in the training data, the true class is always the index with the highest value. So all of these other ones will be smaller. So to make sense of this, you just take kind of the argmax. So that means the index that had the highest value, which in this case is 1. So in this case, you would consider this network to be predicting that the output should be 1. And let's see if we can come back here and actually, that might be happening now. Oh, it's still thinking, but it should be almost done. Now it's just making the predictions, I guess. One other thing I wanted to mention is the softmax function. So if you have something that comes out in a multi-class classification problem, so on some of the wires you'll have negative values, maybe 0, and then what you really care about is the biggest value. So often you want to convert those to probability prediction. So an easy way to do that is to use something called the softmax function. Let me see if I still have this open right here. So the softmax function just, it applies the exponential function to all of the inputs and then divides by the sum of all the inputs raised up with the exponential function applied, which turns each one of these numbers into a probability. So you can see that, you know, 1 is the position with the highest value. So it says that the probability that the corresponding label is the true output is 65%. And then it gives a so all of these add up to 1. So this is a probability distribution. And then the probabilities are just in proportion to how close these other values are to being the highest output. So let's see if this thing is finished. Okay, it did. All right, and so this is what the output from the network looks like. So you can see that for this one, a lot of these values are negative, except that there's a 1 in this position. So that's 0, 1, 2, 3. So it's predicting that 3 is the output for the first one. So let's just see if that's actually true. So it looks like it's wrong about that. Oh wait, sorry. We did this with wide train. So it's actually correct, because here's -1, -1, -1, 1. So this was the true label of the first training instance, and that's also the maximum value that comes out as predicted by the network. And so this is a true prediction. And this 90% accuracy rate is pretty good when you're considering that it's, you know, there are 10 possible classes. It gets the right class 90% of the time. It can beat, I think it can beat logistic regression, and then it gets pretty significantly whipped by random forest on this data set. But of course, you could adjust the hyperparameters and change the behavior a little bit. Okay, so let me stop the